In this video, we're going to cover the second half of section 9.2, where we are comparing two population means where sigma is unknown, and in this case we're going to have equal variances, which is going to change our calculations just a bit. So just as we did before, we should take a look at what the conditions are. The conditions are that the samples are random and independent, both population standard deviations are unknown, both populations are nearly normal or n is greater than or equal to 30. And then in this case, the population variances are assumed to be equal, so we have to pool the variances. And really all this means, again, is that our calculation for standard deviation is just going to be a little bit different than it was when we assumed the variances to be unequal. The point estimate is still x bar 1 minus x bar 2. The margin of error is much more difficult, but again, once we have Excel set up, it's pretty straightforward. Again, one of the main differences is that the degrees of freedom in this case is not the smaller of the 2 minus 1, but is adding the two sample sizes and subtracting 2. Now notice this is how I find the standard error. So it seems really complicated, but really we're taking the first degrees of freedom times the first standard deviation and squaring it, and then the second degrees of freedom times the second standard deviation squared, and then dividing it by the total number of degrees of freedom, and then taking the square root. And then we're taking 1 over n1 plus 1 over n2 and taking the square root. So once we have Excel set up to do that for us, it's going to be very easy. So please don't let the math scare you on this one. And then again, the margin of error is just going to be added and subtracted. So instead of worrying about how scary this looks, remember we're just taking x1 minus x2 and we're either adding this or subtracting it. And again, using that T model for the critical value. So let's take a look at a question together. Obstetricians are concerned that a certain pain reliever may be causing lower birth weights. A medical researcher collects data from a random sample of 12 mothers. So again, we're just going to label as we go through. N1 is 12. Who took the pain reliever while pregnant and calculates the mean birth weight of babies was 5.6 pounds. So that's mean, 5.6 pounds. With a standard deviation of 1.8 pounds. She also collects data from a random sample of 20 mothers who did not take the pain reliever, so N2 is 20. Calculates that the mean birth weight of babies was 6.3 pounds with a standard deviation of 2.1. And this part is key, because the only difference in the two populations, and weight is a normally distributed variable, the only difference between the two populations was the administration of the pain reliever, so it's reasonable to assume that the population variances are the same. So typically they're going to tell you that they're the same or give you enough information that you should be able to determine they're the same. So essentially what they're saying with variances is just the square of the standard deviation. So they're saying, is the spread of the weight between the two groups going to be about the same? And yes, in this case it should be. So assume the distributions of birth weights are approximately normal for both populations. Construct a 99% confidence interval for the true difference between the birth weights. And then of course, does this interval suggest that there's a difference? And this second question is talking about, is 0 in the interval? So let's start at step 1. Again, we're doing this first one by hand, not using Excel. So I've recopied all of the information at the top. Step 1, find the point estimate, which is of course just to subtract the means. 5.6 minus 6.3. That one's really easy because again, we're just finding the difference in the means. And in this case, it's negative 0.7 pounds. Step 2, find that critical value. So remember, the degrees of freedom here is calculated differently because the variances are considered equal, we're going to take n1 plus n2 minus 2. And in this case, that's going to give us 30. And that's just going to change our critical value, because if our degrees of freedom is 30, that just means when we use Excel, or if you're using a t-table, that's fine too, you're looking for 30 degrees of freedom. So t.inverse, remember we're looking at a 99% interval, and so we're actually looking at 0.995 because we take the 99 in the interval and half of whatever's left over, half of alpha, to get the 2.750 for our critical value. Now we're going to actually find the margin of error. And again, it looks scary, but we're going to let a calculator do all of the work for us. So this is why I strongly encourage you to use Excel, because if you're using just a handheld calculator and you're trying to plug all of this in, it's really, really easy to make a mistake. But this is how we're going to calculate it. We're going to take the 2.75, which we found on the previous slide. We're going to take the first n value minus 1, so 12 minus 1, which is 11. We're going to take the corresponding standard deviation and square it. Then we're going to take that added to the second degrees of freedom, so 20 minus 1, times the second standard deviation and squared, and then divide it by the total number of degrees of freedom, which is 12 plus 20 minus 2, which is 30. And then we're going to take that times the square root of 1/12 plus 1/20, those values coming from the sample size. Again, use Excel to do all of that work for you. We find the margin of error to be 2.0035. We're going to subtract that from negative 0.7, which was our point estimate, and then add it to that to end up with negative 2.7 to positive 1.3. And now we're going to interpret what that means. Remember, when we do an interpretation, the first part is to talk about the actual values in the interval in context. So this is part 1. We're 99% confident that the population mean birth weight for babies whose mothers took the pain reliever is between 2.7 pounds less than and 1.3 pounds more than the population birth weight for those mothers who didn't take the pain reliever. That's part 1. Part 2 says, guess what? 0 is between these two values. Again, if you look at a number line, negative 2.7, and then 0, and then 1.3, 0 is between the two values. So since the interval contains 0, there is not sufficient statistical evidence to indicate that the mean birth weights are different for the two populations. Again, for this question, what I'm going to do is I'm going to go through the question that we just did. So I'm not looking yet at the question on your screen. I'm going to look at using Excel to calculate what we just did previously. So again, the degrees of freedom, I'm just going to use everything from the information from down here. So the degrees of freedom is n1 plus n2 minus 2. The point estimate is x bar 1 minus x bar 2. The standard error is the hardest one, so I'm going to come back to that in just a minute. The critical value is equals, and then remember this is t inverse 2 tail, and then I can just take 1 minus the confidence level because that gives me alpha, and then the degrees of freedom. So all of those should match what we just found just a moment ago by hand. The standard error is all of this without that critical value in there. So really it's just a matter of making sure that your parentheses are correct when you put this in. So equals, and now I'm going to do square root, and I'm going to focus on this first one first. So I'm taking n1 minus 1. Now, my suggestion is 3 parentheses. Now notice when you put these in here, you have a black parenthesis and then a red and then a purple. So Excel is going to help you keep track. So I'm going to take n1 minus 1, close that parenthesis. So the purple parentheses are closed, and then times s1 squared. That's s1 squared. and then plus, and then I'm going to do the same thing, parenthesis, which is now purple again, n2 minus 1, close the purple parentheses, times s2 squared, close the red parentheses, because now I need to take all of that, which was my numerator, and divide it by the degrees of freedom, n1 plus n2 minus 2. So I could enter that again, but since I've already done that here for degrees of freedom, I'm just going to choose B9, close the black parentheses, and now that's all of this first portion. Now I need to take that times, and now I need this second portion. So times the square root of 1 divided by n1 plus 1 divided by n2. And then, of course, the margin of error is going to be multiplying those two values. And if you'll recall previously, we had a margin of error of 2.0035, so this matches it exactly. And if you'll notice, negative 2.7 to positive 1.3 is the same interval we had found when we did it previously. So again, we've now used Excel to verify our results. Now we're going to do the same thing. I've already set up all of these cells over here correctly. Just as I did before, now I have two populations. The first one, this is dealing with two populations where you're looking at test scores for people who choose to sit at the front of the class versus people who choose to sit at the back of the class, and whether or not there is a difference. So again, I'm going to just use Excel to find the average of the first population, and then the standard deviation of the sample of the first population, and the count of the first population. And then I'm going to do the exact same thing and now for the second population. Average, standard deviation of the sample, and count. And then the confidence level in this case is 0.9. So again, once I've done that, I get everything else done for me, which is fantastic, but I still need to understand what I found. So the question is, oh, I'm sorry, it wasn't test scores, it was number of hours per week. So we're looking at the number of hours per week studying for a particular math class gathered from people who usually sit at the front versus people who usually sit at the back. So because my first sample was people who sat at the front of the classroom, and all of my interval is positive, I can say that people who sit at the front of the classroom with 90% confidence, I can say that those who sit at the front of the classroom spend on average 1.52 to 5.76 hours more studying per week for mathematics. Because 0 is not contained in the interval, I can say that there is a true difference between the number of hours studied from those sitting in either location. Coming up next, we're going to look at paired data.